Thank you very much for coming, especially given that Liz Rice is giving a talk in K6. It's really great to see all of you here. And let me give you a little introduction into a little CLI tool that I wrote some time ago. It's called Reverse Kube Resource. And yeah, it's a little esoteric, geeky kind of a thing. And what it does is, on the input, it takes a service account, like perfectly, or, well, service account. In this case, it's a service account. It could be any Kubernetes resource. And on the output, it just converts the YAML into a valid, buildable Go with all the properties of the YAML and nothing extra, but using the upstream API packages from Kubernetes. Now, you may be wondering, like, why on earth would anybody want to do that? It doesn't sound like something that naturally a lot of people would want to have a workflow around. And I made an observation that if you exchange applications, if you want to deploy something on your Kubernetes cluster, the odds are you're going to be using some form of YAML, whether Helm or Customize. They are great tools for the getting started, but a little bit less great for the day 2 operations. And the community has started this pattern of writing operators on top of their deployment packages. And most of those operators are currently being written in Go. So there is this little discrepancy that you have defined something in YAML, and then you have your actions written in Go. And I thought, and not only me, some other people also thought that it might be beneficial to actually have it all in one place. So for example, Argo CD does this, and same for Elasticsearch, for Cert Manager. And I actually forgot what this one is. I don't have the speaker's notes for some reason due to technical difficulties, but you have to trust me, this is a noteworthy open source project, Datadog operator, Flux, and it's not only a GitHub fashion trend, it's also happening on the GitLab side, and people just do this. They define their resources in Go, and it makes certain actions a little bit easier. And I myself actually had also a chance. Like the CLI tool, it started more as a curiosity, but in my work, I already had a chance to use it. One project that I actively work on is Schema. That's a Kubernetes extension built by SAP. And they previously extensively used Helm. But recently they decided to move away from Helm, and the deprecation logic and migration logic was written in Go. Bunch of YAML files had to be converted to Go, and I didn't want to do that manually, so I used my reverse kube resource. And another example, so at KKP, there are a couple of ways to extend the KKP. One way in the past was add-ons, which works with Helm and YAMLs. And they're for more elaborate use cases, for slightly not so trivial deployment topologies. You can use a set of controllers that are also written in Go. And with those controllers, so what do I mean by non-trivial topology? You deploy part of your application, for example, in one cluster and part of it in another cluster, which is not the easiest thing to do with Helm. And when you have your operator that is extending the Helm chart, you can do a whole lot of interesting stuff. In this particular case, this was about OpenStack CSI Cinder plugin. We wanted to, of course, you need to deploy the attach detach controller and all the low-level stuff on the nodes. So the daemon set, but the controller, the provisioner, that can live anywhere. So in our case, we decided to put it in a seed cluster. So yeah, definitely you can maintain YAMLs, and it's not that difficult, but I keep the motto, automate everything, close to my heart in Kubernetes, so I decided to automate that. And before we dive into the algorithm itself, I would like to cover and remind us a little bit about some fundamental terminology that I'm going to be using for the rest of the presentation. These are kind of the building blocks of reverse cube resource, codec factory from API machinery, runtime schema, runtime object, meta v1 object, and then core Go packages, reflections, and Go ASD. I wouldn't go too much into details, just kind of give a reminder to everyone who maybe is not using them on a daily basis. So codec factory and TLDR, it uses schema to convert JSONs and YAMLs to the actual data structures, to your pod structure from V1 API. And how does it do it? There's this decode function, so you first have to initialize the codec factory, but then to decode, you pass just a raw set of bytes that you have received from the network or file system for the reverse cube resource case, and it outputs the runtime object and the actual underlying structure and the resource. What is runtime schema? Schema is essentially a map, group version kind, to the runtime objects, and you can build your own schema from scratch, but there is also a client Go where they pre-build the schema for you, and you can use that one for all the core resources that are packed within Kubernetes. For CRDs, or your additional way of extending the API, you need to add them manually to the schema. What is a runtime object? That is an interface that has to be implemented by every single Kubernetes resource. And you actually don't have to write it. You don't have to write these methods. There are code generators provided by the upstream community. And whenever you write a CRD, you use the generator, and it will generate these methods for you. They are the weird files with weird names, ZZZ underscore something. Meta v1 object, not to be confused with a runtime object. Meta v1 object is an interface that allows you to access the metadata of any Kubernetes resource very generically. And now getting to a little bit more geeky stuff, reflections. Reflections are a really, really good way to inspect certain interfaces and get the underlying structure, the data structures behind the interfaces. Now, anybody can make a guess what this is. You don't need to shout it out. Just make a guess in your head. And it's our friend, service account. It's just a representation in binary and hex. And this is the string representation. So if you load your file to memory, if you use OS read file, this will be the set of bytes that will be sitting there. Anyone can make a guess what this is? I'll tell you, it's garbage. Yeah, it's absolutely useless. It's a random part of my RAM memory. And what I wanted to do, use the unsafe package from Go to inspect, after you unmarshal the bytes that you saw previously, into the proper data structures, into proper runtime objects. I wanted to go over the piece of memory, and I wanted to dump it. Turns out that's really difficult. The pointer arithmetics are hard, and there is a reason why the unsafe package is called unsafe, and it's best to avoid it. And actually, it's not all entirely garbage. There is part of the service account loaded in memory. And this is an example of a code that I wrote some time ago. And even I, when I look at it, don't exactly understand how it works at the moment. And I wrote this thing a couple of weeks ago. It uses string arithmetics to get the name of the service account. So in Go, strings, they are not null terminated. They have a string header, and the header contains some values. And you can actually get into the point in memory where the service account name is stored. You can dump it. And here's the example. But it's all depending on the architecture. It's depending on your operating system. I believe it also depends on the alignment of stars and Mars and Jupiter, if they're in alignment. So it's very difficult to do this reproducibly and make a lot of sense out of it. But these bytes, they represent a string header. So the last 8 bytes, that's the length, and hex 18, that's decimal 24. This is a pointer to where the actual bytes of the string name are stored. Another 8 bytes in my architecture. And when I look at the actual address in memory, this is what you would get to see. There is an 8-byte offset, but you can see by the end, there's the beginning of the name. It would be 24 characters long. And if I did more of the pointer arithmetics, I could have acquired the whole name, but I thought this is sufficient and gives the picture. And I think right now is the perfect time to appreciate reflections. Alternative is you could do clever pointer arithmetics, but it's extremely difficult, and there's one thing easy about it, and it's very easy to get it wrong. So reflections, they provide an alternative way to inspect that. So you get any interface, you can call type of or a value of to get various properties of the interface and the underlying structure. With type of, you will get the structure and the package that it imports. With value of, you get the actual content of the interface. And an AST package, that is another thing that last time I used, I think I was still in the university. It's not something that I have an opportunity to use on a daily basis at work, but it's a very powerful thing, and it's good to know about it. And this is an example how to walk a path in Go AST from very, very simple application to the string literal hello ContainerDays. And it's just a path. It's not the full tree. It's pretty long, the tree, even for trivial applications, so it's best not to examine it with a human eye. But luckily, computers, they are good at examining trees, so we can definitely write a clever algorithm. And to give you an example how to walk that path, so file, that means the whole thing. Every file has some top-level declarations. In our case, it's import and the function. Then function declaration has a body, which is a block statement. Body has a list of statements. In our case, it's just one statement. Expression, that expression is a call function expression. And every call function has a part that defines the function, so where it's imported, and the name of the function, and arguments. So there's just one argument that is basic string literal, which is hello ContainerDays. Powerful thing, but also can be a little daunting. And once you get used to it, you can do a lot of interesting stuff. In the case for reverse cube resource, these are the packages that belong to the AST family and that I have used. Mainly, they just make the AST easier to work with. So if you are looking for certain patterns in your extensive code base, you can look up, for example, oh, give me all the structures, or give me all the structures that implement a certain interface. This is something that's kind of a foundation for the support on CRDs for reverse cube resource. And the algorithm. Let's look at how the code is executed. Now, on the left, you can see a bunch of YAML documents. The content at the moment is irrelevant. Important fact is that there can be a bunch of them. The first thing reverse cube resource does, it finds the document separator. It splits and goes for every resource one at a time. So in our case, it's our friend, service account. And then it leverages the API machinery and client Go package to form a schema and codec factory. So we get the runtime object service account. Now, as you can see, it contains a lot of craft. There is a lot of extra information that we don't care about. That's also the reason why it's so difficult to investigate the memory layout of the structure, and especially, for example, maps. So An empty initialized map on my machine is 46 bytes. So if you have a single label and single annotation, that's additional 100 bytes overhead just for having a map. So there's a lot of extra information, and we don't want to write that into a Go file. It would be much more difficult to read than the initial YAML. So what do we do about it? Luckily, API Machinery has additional packages called unstructured, where you can do the same thing. You can unmarshal and marshal to a map of unstructured. It's also a runtime object. This time, it doesn't contain the native data types, but it contains only the essentials. So when we join the two runtime objects, we have a solid foundation for writing out the actual Go file. So we have the data types, we have the imports, and also we have a convenient way to look up what is essential and what we can drop. These are the same things. They just moved from right to left because we'll be finally writing out Go code. And it starts with reflections, and it is heavily going to abuse reflections. The first thing that we know, there is a type, a new resource, new object, and it has some import path. Reflections allow us to see the import path, so we can figure that out easily. And for every resource, reverse cube resource will create a new variable. For now, we don't know the name, but figuring out the name is pretty easy thanks to the object meta from V1 meta API machinery package. So in the comment, I use the exact same string, but for obvious reasons, I can't use the same thing to name a variable in Go because the syntax is very different. So there is some sanitization, convert it to a camel case. And then abusing reflections a little bit more. We recurse into the service account. We know we can skip the type meta because that is already contained by investigating the type of the reflections. So we can safely skip that. And we look into object meta. We know, again, that's a new import. And that's a new field in our output object. And then we recurse again, and we would recurse indefinitely as far as there is a path to walk to. So far, we have hit only the objects that exist in both the top runtime object as well as the bottom unstructured. So name, we can write that down, but we actually skipped generated name. It exists in the top one, but it doesn't exist in the bottom one, so we can safely skip that. Namespace exists in both. And that is where we can actually terminate, because the unstructured tells us there is nothing more to investigate. And one noteworthy package that I use from AST utils, it's for tidying up the imports, so the Go code looks a little bit more idiomatic Go. And voila, that is it. That's how you essentially get to convert YAMLs into Go. And before I go to CRDs, I would like to first tell you something about the sample usage. So how do you currently use the reverse cube resource? You can clone and render your Helm chart, so you have a YAML. Then you feed that YAML into reverse cube resource. The arguments are currently irrelevant and unimportant. It's just the fact that they exist. And then for CRDs, what I wanted as a desired user experience is have a really, really simple way to use it. I didn't want the users to ask them to provide complicated arguments and set up the tool in a convoluted way. So they just pass a path. And the tool itself is walking the file system and traversing it and looking at the code that is present there. And from the code, it should figure out what to register into Schema. Where are all the CRDs defined? And for that, it uses the AST, and it's looking to find certain patterns. One of the patterns is where the group version is defined. Most of the operators, they have something like this, whether they are written using any of the frameworks. And this kind of defines where the CRDs should be registered. And then you have the actual resources. And whenever it's a valid Kubernetes resource, again, it implements the runtime object. So the algorithm, this is just kind of a gist of it. It's comprised a little bit to fit on the screen, but it's not much bigger than this. First, we initialize our AST parsing, and then we check for all of the files and resources there. We iterate over all of the symbols inside of the AST, and we do a lookup whether the underlying object of that certain symbol is a type of a struct. And if it is a type of a struct, then we check if it implements the runtime interface of a runtime object interface. And if it does, we found a CRD, and we know how to register it into Schema. And that is it. You run the previous algorithm exactly the same way. Your CRDs are registered in a Schema, and you get the valid output, and you get the Go file. And something is telling me that I may have been a little too fast. But thank you very much for your attention. Yeah, this is my journey writing this reverse kube resource. And also check out, we just released a new Kubermatic Kubernetes platform. It has applications, and it has a whole lot of new features. It's pretty cool. Thanks.
Okay, thank you very much for your talk. Do we have any questions here? Someone, perhaps? Nobody? Okay. If I may, I have one. How could I say that? What pushes you to build that kind of tooling? I mean, what was the genesis of the whole work you've done on this?
So I think mainly I just wanted to explore reflections and AST parsing, and I was looking for an excuse. And there was a manual task that, yeah, like I think I would have been able to do manual task a little bit faster than writing a tool to automate it. But it was a lot of fun, and I gained a lot of experience, and I'm a lot more comfortable using the AST parsing package. For example, if there's a large code base and you need to add an argument into every single call of the function, you can refactor it by writing 50 lines, maybe less, of a Go scriptlet, and automate the boring tasks, essentially.
Okay, last one for me, I guess. Yep. But anyway, if you have any questions, then please raise your hand and I'll give you the mic. Kind of tough questions. Do you know how many people are using what you built? I mean, did you had any connections, discussions with people saying, hey, you know what, I've used your tool because of this usage, and it helps me in getting, I don't know, this and this and this and this?
Yeah, so it's got 20 stars on GitHub,
nice.
Which is not much. And I guess there's probably one user standing here, but there's fruits of it are used by like 2 companies at the moment, and the operators themselves that had the foundation in the output of the reverse kube resource at SAP, and that is a fairly large company. So yeah, the fruit of it, maybe 2 people use it. I don't know.
Cool. So we have 2 questions on Slido. If you could just take a few minutes to answer them, that would be cool.
Yeah. So does your tool also support converting CRDs only to unstruct, no scheme detection? Scheme detection is currently still work in progress. The algorithm I outlined is something that I have in my head, and I just need to convert it into an actual code. So right now there's this default that it will output as unstruct. But I'm optimistic that whenever I have boring tasks again, I will be able to look at it and finally get it across the finish line. Do you use Go at Kubermatic? If yes, where and how? Extensively, you can look at the Kubermatic repositories, and they are mainly Go. We write automation to manage your clusters. That's like one of our major products. And that is written, I think, purely in Go with some YAMLs. How could be used for custom admission resource controllers? Good question. So the initial drive, why I wrote this was, imagine you have third-party application in Helm that's distributed in Helm, and you want to write some automation in Go, and you don't want to have the two sources of truth where you define your resources in YAML and Helm, and then you render them, and your controllers then operate on top of Go. I thought it might be better to have just one single source of truth and have everything in Go, but you can't really force the upstream to change their strategy, to change how they distribute their software. So this is like a middle point for software engineer, like me, who says, oh, OK, I'm going to do this, hit the button, and then I'll work purely on the Go code. So for the scope of this question, I would dare to say that if you currently, for some admission resource controllers, if you have combination of YAML and Go, and you want to switch purely to one or the other, you can use it to convert from YAML to Go and have just one concise code base.
Thank you very much for answering these questions. Anyone last in the audience?
Thank you very much for staying till the end and not running away.
It was very interesting. Thank you so much. A big round of applause for Jan, please.